So good morning, everyone. I would like to thank the organizing committee and Professor Leonardo Tomazelli for the invitation to be here today. My name is Aline Panazio. I'm from the Federal University of ABC, and I will talk a little about independent vector analysis applied to EEG signal processing. I will start reviewing the problem of blind source separation and independent component analysis and how it can be extended to independent vector analysis. Then I will show how it can be applied to EEG signal processing, especially considering motor imagery paradigm. I will show some initial results that we had applying IVA to transfer learning and conclude this presentation. So if we consider EEG signals are captured by electrodes placed on the scalp, and these electrodes capture a mixture of brain signals that we can consider as our sources. So it's exactly a blind source separation problem, since sources are not known and the way these signals are mixed is also not known. But we use these mixtures, the signal that is captured by the electrodes, to try to separate them and estimate the original sources. So mathematically, we have here S are our sources. A is a linear matrix that mixtures S, and here we have the mixtures X. So our objective here, we don't know S, we don't know A, and we want to estimate W in order to recover the original sources. So ideally, W would be the inverse of A. And to solve this problem, usually we consider S to be independent, so we fall in the independent component analysis framework. And to estimate W, we use independent measures like mutual information or non-Gaussianity like negentropy. This problem can be extended to the joint blind source separation if instead of considering only one set of mixtures, we can consider several set of mixtures. If we consider only one set of mixtures, we are still in the problem of independent component analysis. And the idea here is to consider several sets of mixtures that will be processed simultaneously. And so we have the independent vector analysis. Mathematically, the problem can be modeled in a similar way as previously shown. The only difference is that now we have an index K here that represents the data set. So in IVA, we still want to recover independent signals within a data set, but we consider that can be correlation between different data sets. So here, for example, the first source of the first data set is correlated to the first source of the second data set and correlated to the first source of the third data set and so on. So we can define a source component vector choosing one source from all data sets. So in this vector, we have signals that are correlated with each other. And similarly, we can define a vector using the estimated sources that we call the latent component vector. So using IVA, we want to recover independency within a data set, but we also want to explore the correlation between different data sets to enhance performance. So the cost function continues to be mutual information. And here it minimizes the entropy of all components, but at the same time, it maximizes the mutual information within the latent component vector. Optimization is done using a gradient descent algorithm. And applying this context to EEG, so our objective is to consider several subjects and to process the signal of all these subjects simultaneously at the same time, considering that there may be some correlation between the signals that are captured from each subject. So to do this, we need a very well-defined task, and that's why we chose motor imagery paradigm. In motor imagery, the subject imagines a movement, so it imagines that it's moving the right hand, left hand, foot, and we hope that since it is a very well-defined task, different subjects, for example, imagining that they are moving their right hand, will give rise to EEG signals that present some correlation. And we want to explore this correlation through IVA. So here is our processing pipeline. As EEG data, we used two data sets that are well known in the literature, BCI competition for data set 1, that we named DS1. Here we only used the signals from the 4 humans. We considered 2 classes, right hand and left hand or foot. Signals were collected using 59 channels and 200 trials. And BCI competition 3 dataset 4A that we named DS4A. It has 5 subjects. Signals were collected using 118 channels, but we only used 37 channels that are most related to motor imagery. We also considered 2 classes, right hand and right foot, and 280 trials. For feature extraction, we use the classical autoregressive model. And for classification, we tried 4 different classifiers, support vector machine, k-nearest neighbors, and 2 methods involving deep learning, EEG-net and EEG-inception. So for IVA, in the training step, we considered each subject as being a data set, and we processed the data from all the subjects simultaneously to explore correlation. We applied IVA to each class, so we obtained 2 separating matrices, one W corresponding to the first class and to the second class. But obviously, when we attain the testing stage, we don't know from which class the signal belongs. So we stacked both of these matrices to arrive at only 1 separating matrix for each data set. And then we use this matrix to filter the EEG signal. So here, for example, if Z belongs to the first class, when we filter it by W1, we will have correct components. And when we filter by W2, we will have incorrect components. But this was the solution that we found to be able to process blindly. So after filtering, we extract features through the AR model and use these features as inputs to the classifier. So these are the results that we obtained for DS4A. In the upper part here of the table, we have our benchmark, other methods that are published in the literature. And on the bottom, we have the results that we obtain using IVA with SVM, KNN, EEG-net, and EEG-inception. So EEG-inception had the best result. If we compare with the benchmark, we are the second best. So it's a very interesting result, and it shows that IVA has the potential to enhance classification if we consider the motor imagery paradigm. But another interesting fact about IVA is that it explores the cross-correlation between different data sets. So it gives us the correlation between different subjects. So here to show, as an example, we use DS1, and for example, for subject A, several components are highly correlated with subject B, for example. And the same thing can be done for all the other subjects. So we thought about exploring this information in the context of transfer learning. Transfer learning is the idea of using a machine learning model that is developed for one task, at least as the starting point of a second task. In our context here, our objective is to use a model that is developed for a specific subject and test this model with the data from another subject that is highly correlated with the first one. And to find the best match, we will use the results that are given by IVA, the cross-correlations that are given by IVA. In this case, we used as classifiers the SVM, the LDA, and multilayer perceptron. So here we have a fluxogram of what we did. We start with EEG signals and divide them in training dataset and test dataset. In the training data set, we apply IVA, we obtain the 2 separating matrices, and we train the classifier. But when we apply IVA, we also look at the cross-correlations that are found and establish a rank, and establish with which other subject this first subject is mostly correlated. And then we choose this second subject to test the classifier model that was defined here. So the classifier model is trained with the data from a first subject and is tested with the data from a second subject that is highly correlated with the first one. So here we have the results. Firstly, I show the frequency of the cross-correlation selection. We simulated 20 times. It's still in the S1. And here, for example, for subject A, subject F was the most frequently chosen. It means that it was the most frequently the one that presented the highest cross-correlation with subject A. The same thing happened with subject B. F was also the most chosen. And for subject G. So this is a very interesting result in this data set, since it shows that maybe F can be used as a reference. Maybe if we use the data from F to define a reference model that can afterwards be used with the data from all the other subjects. This is really interesting if we think about brain-computer interface, for example, in which generalization is highly desirable. And for subject F, the mostly chosen was B. So in terms of accuracy, again, in the upper part here of the table, we have all the results that were published in the literature. And on the bottom, the results that we obtained. So with multi-layer perceptron, we achieved the best result. Comparing with literature, we have the second best result. But here, so as I said in the beginning, these are initial results. We are still working on this subject. And we can see that, well, in the literature, usually methods use deep learning. We haven't tried that yet. And for example, for subject B, that is known to be difficult to classify, we obtained a result that beats the benchmark. And we also obtain a very low standard deviation if we compare to the benchmark. So these are interesting results that show that IVA has the potential to be used in this context. So to conclude this presentation, I have shown how IVA can be used to enhance the performance of classification in motor imagery, especially because it explores the correlation between different subjects. And this cross-correlation information can be explored to enhance transfer learning performance. So here we still have a first initial results, but we think that it has the potential to help in this context. I would just like to mention that this work was done in cooperation with Professor Denis Fantinato from UNICAMP and Professor Caroline Moraes from the Federal University of ABC. And thank you. Thank you.